I'm going to define a new set, M. Okay, so we're going to define a new set, M, just to show you the wide variety of things we can apply induction / structural induction to. So let's define a set of strings. So M is a set of strings. Okay, now, so I'm going to tell you something that's in M. Nothing is in M. Okay, the empty string. The empty string is in M. So this is the base case. Okay, and this is the empty string. So the primordial ancestor of M is the empty string. Everything in M is created ultimately from nothing, from the empty string. It's kind of like the Big Bang. Okay, we've got nothing, and then the Big Bang creates everything. Nothing creates everything. Okay. Now, how do I get strings that are in M? Okay, from strings that are known to be in M. So the constructor. Remember, we always have the third rule that nothing else is there. Okay, the minimality rule, the minimality clause. Okay. So if X and Y are in M, so at the moment we only know that epsilon is M, so X and Y are both epsilon. Okay, but if X and Y are in M, then, okay, now this is interesting. I'm going to put parentheses around X and Y. So these I'm going to create strings of parentheses. So I'm going to put an opening parenthesis around X and a closing parenthesis around Y. Opening parenthesis to begin. I'm going to surround X in an opening and a closing parenthesis, and then I'm going to add Y. Okay. So if X and Y are in M, then this strange thing is also in M. Okay, so let's see, what's in M. Let's construct the strings in M. Okay. So we know that M starts off, the primordial ancestor is epsilon. Okay. Good. Now, let's apply the constructor with epsilon. So X and Y are in M, so epsilon and epsilon are in M, so I can replace epsilon here. Okay, so epsilon is nothing, so that puts an open and a close around the first epsilon, and then you append the second epsilon. So we have from this guy, that creates an open epsilon, a close, and an epsilon. But since epsilon is nothing, this is the string of two parentheses, which is open and close. Okay. Interesting. Now we have a second object that's in here. Okay. So we can set either X equal to that or Y equal to that. Okay. So from this guy, now what can we get? We can get, so let epsilon equal X, so we can get epsilon, open, close. Okay, so if I set epsilon equal to X, if I set Y equal to this guy, then I get open and close. Okay, so that means that this thing is in my set M. Okay, so I have this guy. Interesting. Okay, and let's see what else I can construct in M. Well, let me use this guy, and instead of making X equal to epsilon, let me make X equal to this guy. So I'll place an open and a close around this guy. Okay, I'll let Y equal epsilon, so epsilon. But that's nothing, so I got another guy in here. An open, and a close, and a close. Okay. You see, I'm constructing strings which consist of open and closed parentheses. Okay, and now it would be very interesting to try to guess what kinds of strings I'm constructing. So I encourage you to play, and see what else do you get. Okay. I claim, for example, that the following string is in here. So I claim that, open, close, open, close. I claim that guy is in here. Okay, so what's the derivation? Okay, so let's see if we can come up with a derivation. So epsilon is clearly going to, we've already derived this guy. So that gives me this guy. Okay, with X equals epsilon and Y equals epsilon. And then I can get that guy with x equals this guy, the one I just derived, and y equals epsilon. So that gives me, this. With x equals this guy, and y also with x equals epsilon. This guy here with x equals epsilon, and y equals this guy. So order matters in this constructor. Okay? With x equals epsilon and y equals this guy, I get this guy here, which is open. I put an open and a close around x, okay, and then I produce y. Okay, and you see now I've built the inner part here. So if I use this guy as x, so x equals this guy, and y equals epsilon. So what that's going to do is it's going to put an open and a close. It's going to put an open and a close around. It's going to put an open and a close around x, so around this guy, and then produce y, which is nothing. So I get an open and a close around x, which is an open, close, open, close. Okay, and there I've derived this guy. Okay, that proves. Okay, so such a derivation proves that this guy is in my set M because I started from the the primordial ancestor and I applied the constructor rules successively. Okay, and ultimately I end up deriving what I wanted to derive. Okay, question: what about this guy? Okay, open, close, close. Okay. Is that guy in my set M? No. Okay, it's not in my set M. But now the question becomes, how do I prove it? Is it easy to prove? Okay, how would I prove it? That's going to cause some, uncomfortable thoughts because, when you think about how to prove that this guy is not in the set, you realize that you need to show that there's no possible derivation, okay, that can produce this guy. Okay. And how am I going to check every possible derivation? Complicated. Okay. So I'm going to show you an alternate way of proving that this guy is not in the set. And the high-level philosophy is figure out some property that every string in your set has, okay, just like being even. Okay. Use structural induction to prove that every element in your set has that property, and then show that this string violates that property. So since we've shown that every string has that property, and this violates that property, then this cannot be in the set. Okay. So let's try to see what properties do these strings have. Okay. So what properties do the strings of parentheses in M have? Okay, now the obvious thing that seems to be going on here is if you look at the number of red and black, so if you look at the number of open and closed parentheses, they match. There's an equal number of red and there's an equal number of red and black parentheses. We call such a string of parentheses balanced whenever there are an equal number of both. Okay, so balance. That's a property of a string of a string of parentheses. Balance. Okay. Equal number of open and close parentheses. Okay. There's another much stronger property, much stronger than balance, that these strings have. Okay, what's that property? Well, let's look. If you think about arithmetic expressions, you always, whenever you close a parenthesis, you must be closing something that was previously opened. So you never try to close something that was not previously opened. So we can match every closing parenthesis with some opening parenthesis. Okay, so that's another property of a string of parentheses. They can be matched. Okay, what does that mean? That means that every every closing parenthesis, that guy, can be matched with a corresponding opening parenthesis. Okay. Now you can't match, a red close to more than one opening. Okay, so you create distinct pairs of opening. So opening and the corresponding guy that closed it. So opening and the corresponding guy that closes, opening that and the corresponding guy that closed it. In fact, how would we formulate that mathematically? Mathematically, the way we would formulate that is we would say that as you go from left to right in this string, you can count up the number of open parentheses and count up the number of closed parentheses, and the number of open will never be less than the number of closed. Okay, that's a formal way of saying that. But I don't want to get into the details. We sort of intuitively know what it means for the parentheses to be matched from arithmetic. Okay, so these are two properties. I claim that every string in my set M has these two properties. I'm going to prove using structural induction that they have balance. It's an exercise for you to prove that they're all matched. Slightly harder. Okay, so proof of balance. Proof of balance. Proof of balance. Well, we use structural induction, the same philosophy. Okay, so base case. Okay, the primordial ancestors. Okay, so the primordial ancestors. Well, there's only one primordial ancestor, which is epsilon. Epsilon, and it has 0 opening and 0 close, so it's balanced. Is balanced. Boom, check. Okay, so the property that I'm trying to claim for every element in M is this property of balance. Okay, and the primordial ancestor has this property of balance. Now, I need to show that this constructor rule that generates a child from parents, I need to show that this constructor rule preserves balance. Preserves balance. Okay, so I need to show, so the induction step. Show that the constructor rule preserves balance. Okay, and I'm going to underline the word preserves. I keep emphasizing the word preserves. So it's important to understand what it means to show that it preserves balance. You only need to consider the case that your parents have balance. Okay, and it's only in that situation that the constructor has to preserve balance. Okay. So it's kind of like the induction step in regular induction. You assume that the parents have balance, and you now must show that the children have balance. So suppose, so there's only one constructor rule. So suppose X and Y have balance. This property called balance. Now we need to show, so the two parents have balance. We need to show that the constructor produces a child with balance. Need to show X, Y has balance. And it's sort of obvious because there's the same number of opening black and closing red parentheses in X. There's the same number of opening black and closing red in Y. Okay, and you've just added one of each. Okay, so you've increased the number of opening black by 1, and you've increased the number of opening red by 1. So, so the number of opening equals 1 plus the number of opening in X plus the number of opening in Y. Okay. The number of closing equals 1 plus the number of closing in X plus the number of closing y. Okay. But since these two are equal, and these two are equal, then the top sum and the bottom sum are equal. Okay. So these are equal, these are equal, these are equal, and so when you add these three things, it gives you the same result as adding those three things. So these two are equal, proving that the child has balance. Therefore, the child has balance. And that's it. That's the end of the structural induction proof. Because we proved that the constructor rule preserves balance. By induction, every element of M has balance. End of proof. That's the proof mechanics for structural induction. Okay. So just like the orcs. So I just want to emphasize this. Just like the orcs. Okay. Epsilon is balanced. The first two orcs had blue eyes. Okay. And when two orcs get together to produce a new orc, the resulting child, if the two orcs had blue eyes, the resulting child has blue eyes. It's exactly the same. So the entire population that's in M now has blue eyes, i.e. balance. Okay. Okay. Let's consider some more examples. Okay. More examples. By the way, so immediately now we know that this guy is not in M. Why? Because it's not balanced. One opening, two closed. Okay. But let me show you a string of parentheses that is balanced. This guy. So that's balanced. So we might ask, is that guy in my set of parentheses? And that, you can try all kinds of derivations you want. You'll never be able to produce this guy for the simple reason that this guy is not matched in the usual arithmetic sense. So if you take my challenge, okay, and prove that every element of M is matched, that will immediately prove that this guy is not in M. Okay. Hard exercise. And this exercise is in the book. So if you choose to take this on, great. Okay. And then if you want to compare your solution with the solution on the web, fantastic. Okay. So hard exercise. Prove that all strings of matched parentheses are in M. Okay. So this is the other question. Remember, for example, we showed that every multiple of 4 is in A, and it was that more complicated proof with the well-ordering principle, and so on and so forth. Okay. So to prove that all strings of matched parentheses are in M, it's a more sophisticated argument, but you can try to do it. Okay. It's a different question. It's a very different question to asking, is everything in M, matched? That you can prove with structural induction. Structural induction is the tool to prove that everything in a recursive set has some property, not the tool to prove that everything with some property is in M. I hope you realize the difference between those two statements. Okay, more examples. Okay, let's do the speedy race. Bam! Okay, so structural induction on N. More examples. So remember the recursive set N, a formal definition of N. So, which is 1, 2, 3, and so on. So 1 is in N, and if X is in N, then, X plus 1 is in N. Okay. So let's consider some property that we'd like to prove of all the natural numbers. So for example, let's define a property P of N. So it's a property for the natural number N. It's the fact that 5 to the N minus 1 is divisible by 4. Okay. So I'm just claiming this. Okay. So we have a recursive set. We want to prove that every element of N has this property. Structural induction. Step 1. Prove that the primordial ancestor has this property. So base case. So you can use structural induction for any recursively defined set to prove that, all the elements of that set have some property. Okay, so base case, so n equals 1. Okay, so P of 1 is the claim that 5 to the 1 minus 1 is divisible by 4. Well, 5 to the 1 minus 1 is just 4. 4 is divisible by 4? Of course. So this is true. It's true. Okay, so my primordial ancestor has the property, and now I need to show that my constructor rule preserves the property. So if, X has the property P of X, okay, so if X satisfies my claim, so that is, then, so this is the parent, then X plus 1 has the property P of X plus 1. So why X plus 1? Because that's the child. That's the definition of my set. This is the child. So in other words, this constructor rule preserves the property P of N, where N is my integer. So let's see if my parent has the property. So that means that 5 to the X minus 1 is divisible by 4. I need to show that the new child has the property. Okay, so what does this mean? This means that 5 to the X minus 1 is equal to 4K. Okay, it's divisible by 4. So this means that 5 to the X equals 4K plus 1. Multiplying both sides by 5. 5 to the X plus 1 is equal to 20K plus 5. Okay, subtracting 1 from both sides. 5 to the X plus 1 minus 1 is equal to 20K plus 4, which is equal to 4 times 5K plus 1. So it's a multiple of 4. So 5 to the X plus 1 minus 1 is divisible by 4. Okay, so if my parent has the property, then the child has the property. So the property P of N is preserved by the constructor. Okay, and so by induction, the property P holds for all N in my set. That's just a fancy way of saying for every N greater or equal to 1, 5 to the N minus 1 is divisible by 4. We've seen this kind of proof before. It's just regular induction. Induction is induction. So structural induction, when the set that you're trying to prove all elements, so when the set that you're concerned with is the natural numbers, is just ordinary induction with this recursive definition. By the way, there are other definitions, recursive definitions of the natural numbers, and so you can, do structural induction on any valid recursive definition of the natural numbers. That gives you different forms of induction. Okay. Palindromes. Okay. Was it a rat I saw? Was it a rat I saw? Okay, that's called a palindrome. Okay, forget about the capitals and the spaces and so on. Was it a rat I saw? Going backwards, was it a rat I saw? When you say it forwards, when you say it backwards, it's the same. Okay, that's a palindrome. Well, let's focus on binary strings. Okay, so here, 0, 1, 1, 0, 0. Okay, so that's a string. If I reverse the string, so we say that the reversal of this string, 0, 1, 1, 0, 0, when you do the reversal of it, you just reverse it. You do exactly, what we expect. You start from the back and go forward. So this is, the reversal is 0, 0, 1, 1, 0. Well, this string and this string, remember, order matters in a sequence, in a string. So those two strings are not equal. So we say that 0, 1, 1, 0, 0 is not a palindrome. Okay, not a palindrome. Okay. On the other hand, 0, 1, 1, 0, that is a palindrome. Okay. So this is a palindrome. Okay. Because if I reverse it, okay, so I start from the back and move. The reversal of this guy, so I use the superscript R. The reversal of this guy is 0, 1, 1, 0. 0, 1, 1, 0, which match. So these two match. Okay, so that means that it is a palindrome. Okay? So we can consider the set of all binary palindromes. Okay? Well, that's an interesting set, but let me now recursively define some set of binary strings. So let me call this set script P, okay, is a set of binary strings, a set of binary strings, okay, and 1. Tell me something that's in this set. Okay, now this is a case where I'm going to have 3 base cases. So far, we've only seen 1 base case. So 3 base cases. Epsilon, 0, and 1 are all in my set. Okay, so 3 base cases. 1, 2, 3. Okay. There are going to be 2 constructor rules. Okay. So far, everything we've seen, 1 base case, 1 constructor. Now I'm getting complicated. 2 constructor rules. Okay. If X, so X is in P, implies 0x0 is in P. That's constructor rule number 1. Okay. And there's a similar constructor rule where I can, so here what I'm taking X and putting a 0 on the front and a 0 on the back. Okay, and here what am I doing? I'm taking an X. I'm going to take X. If that's in my set P, okay, I can prepend and append 1. So 1, X, 1 is in P. Okay. So let's see. What are some of the strings in P? Okay, what are some of the strings that are in P? So let's construct some of the strings in P. Okay, so P equals, we start with epsilon, 0, and 1. Now I can take anything that's in here and I can attach 0 to both sides or 1 to both sides. So let me take all of these and attach 0 to both sides. Well, if I take this guy and attach 0 to both sides, you get 0, epsilon 0, which is 0, 0. So I get, now in my first, think of this as the first generation. I get 0, 0 or 1, 1, appending 1. If I append 0 or 1 to this guy, I get 0, 0, 0, 1, 0, 1. If I append 0 or 1 to this guy, I get 0, 1, 0, 1, 0, 1, 1, 1. First generation. Now I can repeat. Okay, but observe that every string that was generated, okay, has every string that was generated is a palindrome. Okay, so claim. Okay. Every string in P is a palindrome. Let's prove it. Okay. Structural induction. Let's look at the base cases. So structural induction, base cases. In this case, base cases. Because I have more than 1. So let's do all the base cases. Well, these are all palindromes. So these are all palindromes. So just like the first orcs had blue eyes, my primordial ancestors are all palindromes. Now, I need to prove that the constructor rules, preserve palindromicity. Okay. So, prove that constructors preserve palindromicity. I don't know if I just invented a word. Okay, so prove this. Now comes the interesting new step. Well, because we have more than one constructor, we have multiple constructors, we have to prove it for every constructor. Not just, you don't just get to pick which constructor you want. We have to prove it for every constructor. So let's see. Okay, let's take a palindrome let's suppose that the parent is a palindrome, so 0, 1, 1, 0. So 0, 1, 1, 0. Okay, and what's the child? The child in rule 1 produces, add 0 on both sides, so you get 0, 0, 1, 1, 0, 0. Okay, and so the parent was a palindrome, the child is a palindrome. Okay. 2. Okay, you have 0, 1, 1, 0, and if you append 1, so that's the second constructor rule, you get 1, 0, 1, 1, 0, 1. Again, another palindrome, going backward. In general, if you have a palindrome X, and you attach 0 on both sides, now let's see what it means to take the reversal of that. The reversal of that, okay, it means you start from the back and read towards the front. So you start from the back, you get 0. Okay, now you start reading X from the back to the front. So that's just x reversal. Okay? And then you end up with a 0. But if you started with a palindrome, x reversal equals x. So this is just x. If you start with a palindrome, then the reversal is a palindrome. So this is 0x0 if x equals xr. That means that if you started with a palindrome and added 0 to both sides, you end up with a palindrome. You can make the same argument for if you started with a palindrome and added 1 to both sides. What am I arguing? I'm arguing that the base cases are palindromes and the constructor rules, 2 of them now. The constructor rules preserve palindromicity. That's what you need to claim by induction, more specifically by structural induction, that, this set that we constructed has all palindromes. Sorry, this set that we constructed, everything in this set is a palindrome. And now I leave you to fill in the details. So everything in P is a palindrome. Tough exercise for those of you who want the challenge. Prove that every palindrome is in P. That's the harder second kind of question. Everything that's a palindrome is in P. Prove. Exercise. So exercise. Prove every palindrome is in P. So in other words, this is a recursive definition of the set of palindromes. Everything in here is a palindrome, and everything that's a palindrome is in here. Okay? Let's do one more exercise. Arithmetic strings. Arithmetic string. So imagine, a set A of strings, and these strings are going to be made up of, parentheses, the digit 1, and addition and multiplication. So 1. The number 1 is in A. Now we're going to view this number 1 as a string. And 2. There are 2 constructors. If X is in A, constructs. So if you have something that's in A, you construct a string which is an open parentheses, X plus 1 is in A. Okay, so that's my first constructor. I can define any set I want, so I'm defining a set. Let's see what it is. My second constructor. If X and Y are in A, then in parentheses, X times Y is in A. Okay, so let's see what's in A. Well, 1 is in A, so A equals 1. And then now 1 is in A, so you get 1 plus 1 plus 1, and 1 are in A, so you get 1 times 1. Interesting. Okay. And now, since these 2 are in A, we can immediately get, for example, that 1 plus 1 plus 1 times 1 times 1, is in A. Okay. And we can get that, 1 plus 1 plus 1 times 1 plus 1 plus 1 is in A. So this is X, this is Y. Okay. And so on. So you see, it's generating arithmetic expressions. Let's evaluate these expressions in the usual way that we know how. So this is 1. This is 3. So we have 3 and 1 here. This is 3 times 1, which is 3. This is 3 times 3, which is 9. Okay. Looks like, everything in here is an odd number, and indeed that's the case. Claim. All the arithmetic expressions in A, all the arithmetic expressions in A evaluate to an odd number. Okay, so let's see if this is true. Well, the base case is clearly true. Base case. Primordial ancestor. Base case. Clearly true. Okay. Now, I'm just going to show you that constructors preserve oddness. So constructors preserve oddness. Okay, I'm just calling this property oddness. Okay. And I said constructors because I have 2, so I have to show it for both of them. But let's see. if x is odd, so if the parent is odd, is that preserved in the child? Well, we have odd plus 2. So odd plus 2 is odd. So this rule preserves oddness. If the parents are odd in this rule, x and y are both odd, then the child is the product. The product of two odd numbers, but the product of two odd numbers is odd. So this constructor preserves oddness. So the constructors preserve oddness? Yes. Now I leave you to fill in the details to prove all this, but that's all you need. That's the idea of structural induction. The primordial ancestors have your property, and procreation preserves the property. Okay? So, done. I've shown you the basic idea. Let's do a speedy race, and now come back and prove something about trees. Okay? For which we gave a recursive definition of a structure. Okay? Wow!